All right, so time for the next speaker. That is Katarina Söderström from FY, Sweden. She will talk about laboratory measurements of radioxenon samples from an IMS station. So, please, Katarina.
So then we'll turn from particulates to radioxenon. We've then performed a comparative study remeasuring xenon samples from our IMS station in our radionuclide laboratory. And the objectives of this is really to try to improve the use of the radionuclide laboratories within the IMS, because they are not regularly used. They are not used for routine measurements, mainly for spike measurements. And we think that we could have really use of sending radioxenon samples to labs to get better classification and verification of the radioxenon detections. So at FY, then we run one IMS station, and we also have a laboratory system. And both these systems are sauna systems. And the IMS station is a sauna 3 system. It was upgraded a couple of years ago from a sauna 2 system. And the sauna 3 then runs with a 6 hours collection time, 6 hours measurement time. And the sample volume, for example, corresponds to about 40 cubic meters of air. And then beta gamma detection. And the laboratory system is also a sauna system. So it's basically the same as the IMS system, except for that it doesn't have the sampling part. And our laboratory system is not part of the radionuclide laboratories within the IMS, but we still participate in the proficiency test exercises run by the CTBTO. And if we compare then the laboratory system to the IMS system, we have an improved GC calibration accuracy, so we can determine the xenon volumes more accurate. We also have a thicker lead shield, so that we get a lower background. And we can then manually choose measurement times, so that we can adjust them to the sample measured. So this study was then performed over a period of about a year. We took totally 91 samples from the station and reran them at the laboratory. And then so the graph shows the total number of samples at the IMS system with the light blue, with the activity concentration of 133 at the y-axis. And then the blue circled ones are, dark blue circled ones are the ones we remeasured at the laboratory. And we compare then results for xenon volume determinations and also for the activity concentrations. Starting then with the xenon volume determinations, we can see that we measured the xenon volume at 2 times at each system, before and after the measurements in the detector. And we have a small loss of xenon in each step during the process, but it's a constant loss, and the xenon volumes measured between the 2 systems shows a linear correlation. You can also see that we have much better accuracy than for the xenon volume determinations at the laboratory system than compared to the IMS system. So if we then move on to the activity concentration results, we measured 133 in almost all the samples, or at least big amount of them, rather high concentrations. About 90%, more than 90% of the samples had activity concentrations above the MDC. For 131M, we also had quite a few samples detected above MDC. About 50% of these detections were above the MDC compared to above the LC as shown in the table. For 133M and 135M, we had no detections above the MDC in either of the systems. So I will not talk much more about those 2 nuclides. I will concentrate on the 131 and 133. So starting then with the 133, we see we have a very linear relationship. On the x-axis is the measurement, the activity concentration from the IMS system, and on the y-axis then is the corresponding one for the laboratory system. So we see that we have a linear relationship along the whole span of activity concentration measured. A bit higher at the laboratory system, but it's really within the uncertainty. And then if we turn instead to 131M, we still have a linear relationship between the two systems, but we have a much higher, about 25% higher result for the laboratory system than for the IMS system. And as I said, we participate in the PTEs, and we have not seen this discrepancy for those measurements, so we trust the laboratory system given the correct results. So we try to look a bit into what could make this strange behavior. And the MDC for the 131M is really depending on the concentration of 133 in the sample. So if we have a lot of 133, we get a lot of interference since the region of interest for these two isotopes interfere. These interference correction factors are established during the calibration of the system. But we looked a bit into this and see if we adjust those factors a bit, we can get a much better relationship, reduce the bias to about 10% with just a very small reduction of this correlation factor. And this is just a first estimate of what this could depend on. We probably need to look at these correspondence a bit more. So we're trying to look also into the MDCs of the systems. If we want to measure the system at the laboratory, it has to be sent there, and you need to have the good MDC to be able to measure something better. I'll just skip this and go to the next. So we have been looking then at how the delay time, or the time between the collection and the measurement affects the MDC for the systems. And for the IMS system, the MDC is more or less constant, at least when you have a low concentration of 133. These are the crosses, the MDC for the IMS system. And then the dots represent then the measured MDCs for the 4 other radionuclides, or for the laboratory system. And we can see that up to a week, we have lower MDCs at the laboratory than at the IMS station. And then if you increase the measurement time even more, standard measurement for these laboratory measurements were 11 hours. If we increase the measurement time, we can see that we have even lower MDCs. These are the 2 points that are encircled in this graph. So then we also try to look at, because the last graph was for then when we had a low concentration of 133, so we would like to see how it looks if you have a higher concentration of 133 when we have this interference. One idea was that if 1M or 133 has the half-life differs a lot, so maybe if we wait longer, the ratio of 131M would be higher compared to 133, and that this could be better than for detection of 131M. So that's the green lines in the top of the graph. When you see that you get quite a small effect on the MDC for the system, compared to if you increase the measurement time. That was shown in the red curves. So if you increase the measurement time, you really can reduce the MDCs for the 131M. So that's a much more efficient way to go, to just measure longer. So in conclusion then, we think that the IMS laboratories could be used for remeasurement of radioxenons samples, and that the transport time could be compensated for, since you have a much more better possibility to adjust and modify the measurement at the laboratory to increase the detection limit. We also think that the laboratory systems can be very good to have as a QC quality control for the IMS systems. And also that if we have a better second determination of the radionuclide activity concentrations, we can also get a better estimation of the xenon ratios, so the ratios between the different xenon isotopes. So, thank you.
Thank you very much, Katarina. So, questions? It was very clear. Okay. Yes, Rita.
I was curious, you was talking about minimal detection concentration or limit concentration, because in one of your slides it was both, so I do not remember in which slide, but, but it was minimal detection concentration, yes?
Yes, the last slides were minimal detected concentrations, MDCs, yes.
Okay.
All right, okay, you have one?
So there's an online comment. I haven't read it yet, so I will do it live. Thank you, Katarina, for an excellent presentation. I wondered, based on the measurements you have completed, at what point in time are the benefits of remeasurement on a laboratory system no longer significant enough to warrant the sample shipment? Whilst we can count for longer, at some point it may not sufficiently counteract the decay in activity. Perhaps you could indicate an approximate length of time, and that was met.
That depends really a lot on the initial activity in the sample, because so I think it really depends. We've seen that up to 7 days with our measurements, we can have a better MDC, but then if you have a very low concentration from the beginning, you get below the, so that I think it's really much depends on the activity in the sample from the beginning.
Right, I see no more questions, so thank you again, Katarina.
Thank you.